Section 6, Exponential and Logarithmic Equations and Inequalities. Exponential equations. An equation in which the variable occurs in the exponent of an expression is called an exponential equation. So for solving exponential equations, you want to isolate the exponential expression on one side of the equation, then take a logarithm of each side, Step 3, apply either the inverse properties or the power rule, and then solve for your variable. And we solved a few of these equations in a previous video, like the two we see below. So if I wanted to solve for x here, what I would need to do is I would first need to isolate e to the x, which I can do by dividing by 4. So now I have e to the x equals 5 over 4. And then I need to take the log of each side, and I need log with the same base as my exponent. So for this problem, that's going to be the natural log. So I take the natural log of each side, apply the inverse property here to get the x out, and I have x equals ln of 5/4, which if you plug that into your calculator is roughly 0.223. And if this were a written exam that I was grading, I would accept either of these answers. The second one I have here, we need to kind of do the same thing. So let's start by dividing away the 3. If you want, you can pause the video and try this one on your own and then check your work. That leaves me with 2 to the x minus 2 equals 33. The base of my exponential is 2, so I need to take log base 2. This leaves me with the exponent here, x minus 2 equals log base 2 of 33. Moving the 2 to the other side, it's a positive 2 and a positive log. And if you want to evaluate what log base 2 of 33 is, you should utilize the change of base formula. So in your calculator, you can type in log 33 over log of 2, which is approximately 5.044. So our answer down here, if I add 2 to that, will be approximately 7.044. Exercise 2. The number of Atlantic bluefin tuna in thousands, x years after 1974, can be modeled by f of x equals 230 times 0.881 to power x. Estimate the year when the number of bluefin tuna reached 95,000. All right, well, they gave us this function, f of x equals 230 times 0.881 to power x. And we're trying to estimate the year when the number of tuna reached 95,000. Well, x represents years after 1974. So we're trying to solve kind of for x here. And we're told that for whatever that x value is, this will be equal to 95,000. So I can think of this as 95 equals 230 times 0.881 to power x. And now it just looks like an exponential equation that I need to solve. So I'll start by dividing the 230. Also, I didn't write 95,000 because this equation was given to us for tuna in thousands, so it's already taken care of. When I divide that in my calculator, I get 0.413 equals 0.881 to power x. And now I need to get rid of the fact that my x is in my exponent. I need to get it out. And I'm going to end up using the natural log, which is something you can do. As long as you take the same log of both sides, it doesn't necessarily need to be, for example, log base 0.881, though that will work. I can utilize my natural log to still take my variable out and solve for x. So I'm going to take ln of both sides so you can see how this will work. Now, what's different here than in the other problems I did is normally when I would take a log, I use a log that has the same base as the base of my exponent, and then I utilize an inverse property to say that it's equal to whatever I had in the exponent. Here, I'm going to use my power rule. So if you recall, if I have a log with a power, I can instead write the power in the front and it's being multiplied. So these are the same. So ln of 0.881 to power x is the same as x times ln of 0.881. And then to solve for x, all I need to do is divide away this ln of 0.881, because that's just a number, right? It's e to some power gives us this 0.881. And that power is what that log is showing. So now in your calculator, you want to do ln of 0.413 divided by ln of 0.881, and that'll give you x. And if you plug that in, you get x is approximately equal to 6.9797, or I'm going to say almost 7. So estimate the year when the number of bluefin tuna reaches 95,000. It's going to be 7 years after 1974. So I expect this to happen in 1981. I think that's pretty cool how you can just use the natural log and then utilize the power rule. But if you wanted to do it the way we've been doing it, you definitely could have done log base 0.881 of 0.413 and then log of that same base on the other side. It would have left you with x, and then you have log base 0.881 to 0.413, and you would utilize the change of base formula to say that this thing was the same as log of 0.413 divided by log of 0.881, and again you'd get that same number. So either method will work just fine. I'm very familiar with using the method where you utilize ln, especially when the base is such an ugly number like this 0.881, but either one is okay. All right, here's some other exponential equations that look a little different than the ones we've been doing. Notice on this first one in exercise 3 that we have two exponential expressions, but they're each base 5. Well, if you have the same base, then that implies that your exponents should also be the same. So same base implies I should have the same exponent. So what I can do is I can just set the exponents equal to each other and solve. So let's subtract x to the other side, and I get back x equals -3. And you could check, if you plug in -3, 2 times -3 is -6, -3 minus -3 is -6, so it does say 5 to the -6 equals 5 to the -6. On this second one, I want to do something similar in that I want to make the bases look the same. So 16 is the same as 4 squared. So I can rewrite the left-hand side as 4 squared to power x. And then if you have a power to a power, that's the same as multiplying your powers. So take a second and pause the video and solve the equation from here in the same way that we solved the first one. And you should get back x equals 2/3. Exercise 4. We have e to the 2x minus 3 times e to the x plus 2 equals 0. Maybe some of you look at this and think that this almost looks quadratic, or at least it has kind of a similar setup to the equations we've done previously where we utilized a substitution. Remember I told you that if the term in the center has a power that's half the power of the first term, then you can make it look quadratic by using a substitution like u equals my middle term, and then if I square both sides, I end up with u squared equals e to the, well, if I have a power to a power, I can multiply them, so I get 2x. So I see that u squared will be e to the 2x, and lucky for us, that's exactly what I have here. So I can go substitute in u squared for e to the 2x and u for e to the x, and I can leave everything else the way it was. And now it just looks quadratic, which we know how to solve. We just need to factor this. Set them equal to 0. Solve for u. But remember, we made a substitution, so we need to substitute back. And u is the same as e to the x. So I really have e to the x equals 2 and e to the x equals 1. To get the x out of the variable, I can take the natural log of both sides. And I get back x equals the natural log of 2 and x equals the natural log of 1. I'm going to take this answer, and then this is asking e to what power gives you 1, and that would be e to power 0, so I am going to simplify this down to x equals 0. You could also plug this into your calculator to get these answers, and you could get the decimal answer for this as well. Solving logarithmic equations symbolically. Step 1, isolate the logarithmic expression on one side of the equation. This may require utilizing properties of logarithms. Step 2, exponentiate each side of the equation with the same base as the logarithm. Then apply the inverse property, solve for the variable, and check your answer. Exercise 5. Here I have ln of 4x equals 1.5. Well, the base of ln is e, so what I need to do is I need to take e to power ln of 4x equals e to power 1.5. And remember I showed you this earlier that I just get kind of lazy, so I just put the base underneath the equation so that they look like powers. Now using my inverse property, this allows me to pull out that 4x, and I have 4x equals e to power 1.5. Divide both sides by 4, and you get back x equals e to the 1.5 power divided by 4, which in your calculator is approximately 1.12. Our second one here, we need to utilize our properties of logs in order to get this into one log, which we can do because they're both base 10, so the bases match. Now, since they're being added, this means that I can also write it as log base 10 of these items being multiplied, or log base 10 of 2x squared. Now I've been saying log base 10, so I know the base is 10, so I need to make the base of my exponential part 10. So I have 10 to power log 2x squared equals 10 to power 2. Using my inverse property, this allows me to get back what was inside, which was 2x squared. So 2x squared equals 10 to power 2, or 2x squared equals 100. Dividing by 2, I get x squared equals 50. Now let's take the square root of both sides, and I get x equals plus or minus the square root of 50. But let's just wait for a second and go look back up at our original problem, because we are supposed to check our work, which I didn't do over here, but let's at least do it here. So let me check if I plug in negative square root of 50. Just think for a second, what is this really asking? It's asking 10 to what power is negative square root of 50? And there's no power of 10 that's going to give me back a negative, right? If I plug in a positive value, I'm going to get back an even bigger positive number, unless it was like a fraction. It's still going to be positive though. If I plug in a negative exponent, I'm just going to get 1 over 10 to some power. So I'm never going to get back this negative. So the negative one doesn't work. So really, I should only have x equals positive square root of 50, which if I plug into both of those, will work. So negative does not work. Things like this is why it's important to check your answers for these types of equations. All right, this last one, we may need to first combine our logs together. So over here we have addition, which means these logs, which are both base 5, can be written as multiplication. And now that it's written in this way, why don't you take a second on your own and pause the video and try to solve this by using the base of the log as the base of your exponential on both sides, and then working out to find what x is. So take a second, pause the video, and then come back and check your work. And you should get that x equals 4. So what I did was I noticed that the base of the log was 5, so the exponent's base I needed to use was 5. So I made my logs the exponents of my base 5 exponential expressions. Using my inverse property, that just left me with what was inside the logs, which is x plus 1 times x minus 1 equals 15. Multiplying this out, I'm left with x squared minus 1 equals 15. I added 1 to both sides. Now I have x squared equals 16. I took the square root of both sides to give me back x equals plus or minus 4, but then I just checked the negative like we did last time by plugging it into one of my original equations here. And when I do that, it gives me back a negative inside my log, which isn't going to work. And notice if I plug in the positive 4 to either of those, I'm going to get back something positive inside, which is okay. On the other one, when I do that as well, I still, even though I'm subtracting 1, I still get back positive 3, so that one's also okay. And you can see that this actually does equal log base 5 of 15, because you can utilize the rule where you end up making this multiplication. And 3 times 5 is 15. So the one that works here is just x equals positive 4. Exercise 6. Let's solve negative 2 e to the x plus 1 is greater than negative 1. I'm going to start by getting the e to the x by itself. So subtract the negative 1. And then divide away that negative 2. When you divide by a negative, make sure that you flip your inequality symbol. So I'm trying to figure out where e to the x is less than 1. And I can utilize a graph to figure this out. So I'm going to graph each side. I'm going to graph y equals e to the x. And I'm going to graph y equals 1. And then use my graph to figure out where my e to the x graph is less than my 1 graph. Well, here's y equals 1. And we've drawn some exponential functions quite a bit now, so we know that we're going to go through the point 0, 1, and e to the 1 is going to be e, so 1e, which is 2.7 something. And I should get something that looks like this. So this is my e to the x, the other one is 1. So on this graph, where is e to the x under or less than my graph y equals 1? Well, that's going to be from here this way. Or in terms of x values, it's going to be when x is from negative infinity up until x equals 0. At x equals 0, these two graphs are equal, which I don't want. I want strictly less than. So this is going to happen when I'm less than x equals 0, or from negative infinity to 0, not included. Okay, let's try a logarithmic inequality. So here I have log of x is greater than or equal to 3. Well, let's just start by figuring out where log of x is equal to 3. So remember, you can't see the base here, but there's kind of an invisible 10. So I'm really asking 10 to the power 3 equals x. So if I want to solve for x, I need to evaluate 10 to the power 3, and I get back x equals 1,000. Now I'm not going to graph this super accurately, but we know the basic shape of our log, right? It has this vertical asymptote at the y-axis. It's going to cross through the point 1, 0, and it goes off in this direction. Now this is not going to be to scale at all, but let's draw the line y equals 3. Let's say it's here. Okay, so at some point, we'll say right here, our red graph does go above the green graph. So this is y equals 3. And the red graph is log base 10 of x. And we saw that these two graphs are going to be equal when x equals 1,000. So this is the coordinate 1,000, 3. So after x equals 1,000, this graph is continuing to go up, or this graph is above the line y equals 3. So where is log of x going to be greater than or equal to 3? Well, it starts at 1,000, and from that point on, the red graph, or log of x, is greater than or above the graph y equals 3.